Good.
You guys ready?
Okay, I think we should start. So I should say that I'm very grateful to Sabrina for agreeing to present these 2 lectures, and you have our undivided attention.
Okay, at least for me to maintain. Great. Okay, so I'll just start writing this triangle of relations and features that come up when you're studying massless scattering. So you have some lectures. Hey,
Hello.
we got you to come. So
Exactly. Well, I came back just for you.
memory effect.
You fine.
So I like to start out with just putting this up on the board because it's kind of a good thing to keep in mind when we go through things that are maybe a little bit more just technical versus more interesting. Personally, I love memory effects, so that's what I get to talk about next time. But when you're studying massless scattering and you're looking at like a low frequency limit of the extra attached gauge particle, or in position space really far away, these 3 features kind of come together. So because it's a amplitudes focused workshop, I'm going to not really spend too much time describing like the origins of showing like that soft factors are universal or which ones seem to hold beyond tree level. But they connect in a nice way to some physical observables that you can see if you look at a long time limit of like measuring something, which I'll get into, but exactly that something is next time. And also asymptotic symmetry. So today the title is Null Infinity because I'm going to be explaining a little bit about the arena where these asymptotic symmetries live, which are related to the original expressions of, if you've seen work by Strominger and collaborators, including self, expressing things as ward identities using soft factors. So this connection was kind of the first one, but it's all about massless scattering and what happens near null infinity, which is the topic of today. Great, okay. So right before I get into flat space, because we're going to study scattering in asymptotically flat space, which is what I'll explain today, it's good to get a sense of how many times this repeated thing comes about so that we can look at simpler examples or more complicated examples, such as like superrotations and gravity. So that's the topic of today, getting into that. But even if you just have a photon, so some U1 gauge particle in flat space, you still have Weinberg's soft factor for that. And you can see there's going to be this large U1 residual gauge symmetry, which is actually going to correspond to some net acceleration or particles giving you some changes for a test charge far away from the memory effect. And this triangle has been filled out at different times from the 1950s from some subleading soft factors by Low to more recently. And the recent example I just want to give to kind of set, if there's any, like people want to look up more into it, is the subleading soft graviton theorem, which Kuchazo had worked on with Andy Strominger. So that's 491. And that leads to this superrotations as it kind of like suggested, the 2 works to each other to suggest that maybe there's something to it. Because a lot of them were known before, but these were relatively new. So if you look at the 14 versus 1960, you can get a sense of that why this might be interesting, because so many of these were just in the past few years noticed, and they all kind of fit together. And this is that iteration of the triangles for spin memory and also there's superrotation symmetries, which is what I will start to get into next. So before we go into some of the more technical details for what I want to say is like asymptotically flat spacetimes, we're going to talk about flat spacetimes to begin with. So we're studying massless scattering, So it's natural, in 4 dimensions for now, to look at advanced and retarded coordinates. So we'll define U as P plus R and V C plus R. And if we want to then just set up our conventions and draw a Penrose diagram, we can actually rescale these coordinates and define, say this is tangent of a big U with big V. And in that case, our flat space metric ends up taking a nice form. So I'm just kind of writing out the transformations to coordinates where you can plot what I'll show as a Penrose diagram for flat space so that we get a sense of this null boundary. Okay, great. So I want to draw all of my Minkowski space, a finite diagram, and then talk about the structure. So by changing coordinates such that now these range from negative pi over 2 to pi over 2, and I'm doubling, so if there's going to be a sphere here, so S2, you could think of scattering looking at the sphere surrounding you. This is going to be North Pole and South Pole, say, on the opposite sides of the diagram. And the point of this is that you have, say, a time-like observer, so if you're just sitting, you come in from past time-like infinity, and you would go up to future time-like infinity. But what we're interested in is massless scattering. And what's curious about Minkowski space is that where massless scatterers would actually come in is along the null boundary. So we'll call this square minus and square plus. And there's spatial infinity over here. And so the point of just going through this exercise of writing down flat space in terms of these coordinates is that we see that where this prefactor diverges is actually null. So when u equals, so the cosine of u vanishes, so pi over 2 or plus or minus pi over 2, here it's actually a null boundary. So that's something good to point out because we want to now think about massless scattering. And so we're imagining comparing some in-states of massive particles to some out-states of massive particles. And if we think about some interaction occurring somewhere in here, and then tracing back to where they started out versus where they end up, you can imagine that there's a natural sense in which you can look at preparing the states along past null infinity, and then looking or observing near future null infinity. And so part of the setup is to get some notions for when now you have a space, and this is actually Minkowski space, so this is like flat metric. I just rewrote it in terms of strange coordinates, so I could put it in this form. But if you have now some notion where perhaps something complicated goes on here, even if, like especially if you're dealing now, say, with gravity, there is a way in which, so like starting from work in the 1960s by Bondi, Vandenberg, Messner, and Sachs, that you could still keep this boundary and hope that whatever happens in the interior asymptotes to being close enough to being flat, that you can still basically attach a null boundary to your spacetime and study it in that way. And in the 1980s, like work by Ashtekar tried to, or formalized the notion of, say, going from data on a space like Cauchy slice to connections as a space on null infinity. And so there's going to be a talk later today, which is an ambitwister strings, which isn't, it's not going to deal with the same thing exactly, but it does in some sense associate phase space with null infinity. So it'll be kind of cool timing to like pair those together. And then, okay, good. So basically, essence of this is there's a null boundary, and we want to think of data living near the null boundary. And if we were just dealing with some iterations such as photon scattering or like scattering off of charged particles, then you could just deal with flat space as it is. But if we want to then add some gravity and look at like Weinberg's self-graviton theorem, it's natural to think of this picture where we replace Minkowski space with something that isn't Minkowski in the interior, but asymptotes. And today I'll try to explain a little bit more about exactly what we mean by like what fall-offs you need to reach that point. So a little bit more on conventions. I'm going to be describing this angular part in terms of stereographic coordinates. So you're going to see a lot of z's and z bars. Okay, so you have your just phi and theta on the sphere. And so this is the projected coordinates we're using. And then the metric, I'm going to write with this little gamma so that it doesn't surprise people in the future. Great. And if I write dz anywhere, this is going to be a covariant derivative with respect to the S2. And if I wanted to describe, say, at some point later, we'll talk about massless particles and their form momenta. If you were going to compare it to soft vectors, so for reference, we can just write down what that guy would look like. So you have some overall energy scale and a direction on the sphere that parameterize your massless form momentum. So this is just for conventions. And so as you can see here with the denominator canceling, that is just energy is the first component and the next by Z. But this is what it looks like in terms of Z stereographic, in case lots of things are going to involve Z's. It becomes nice because a certain component of the metric, which is going to be the ZZ bar, or the ZZ component is going to be the, like what you think of as the two helicity states of the So I mentioned flat space, and now I'm going to talk about asymptotic flat space. And that involves a rather complicated looking metric, but I'll write it out, and it's going to be kind of long, but then we'll make sense of each of the terms and carry on from there. So stay out of the shadow.
Actually, before, I don't know if you plan to say it, but before you go to asymptotically flat, in flat space, if you deal with U1, can you sketch the story quickly?
Oh, you want to sketch the story for the U1 case? Okay, I was hoping.
In words, I mean, if it can be done in a couple of minutes, then do it. If
I was going to hopefully put it with the memory effects, because one thing I said about the U1 case is basically, after today, we're going to hopefully get to just constraint equations for, like it's going to be a set of equations for the gravitational case, which is the more complicated for dealing with null infinity. And there's also going to be a similar one for the U1 case. So I can say what you do, but tomorrow I'll write out the equations and then show the soft vectors, because the intuition is more for when you have, what do you measure, what's the radiation you see. And so like that you get into that really nicely versus otherwise. So what I write here for the gravitational case, well, I'll explain it and then say how that also holds for the U1 case, because, okay, in the U1 case you have a gauge field A, and in this case we have the metric. So what happens is you basically assume some 1/r scaling. And maybe it's more intuitive for if you, like when you study electromagnetism for the first time, you talk about radiation fields. So you have this 1/r squared Coulomb field, and then you have a 1/r field when you take a charge, shake it, and it moves. And so it's like when you like think about the fields there, it's kind of natural that you would have like, okay, I have a 1/r field for the radiation and 1/r squared, and I can look at higher multiple moments and decompose them in terms of different radial falls. And so essentially what's going on here is that when you're really far away and you look at past, so say you're sitting as a large observer, and you're looking back at what's happened in the interior, then there's a natural, the coordinate you have is the same along like where that radiation is coming at you, tracing back to the acceleration. So in the natural sense, as a larger observer, you're seeing the leading fields, so like the ones that fall off slowest in 1 over r, so that's what you see. And the setup tomorrow, which will go into memory effect, is kind of actually translating what you could measure with like how like test charges would accelerate as a result of the scattering process. And these net effects in terms of the charges that enter and leave. So that's going to be a connection between like the soft factors there and the memory effects, but the essence is a 1 over r expansion. Is there anything in particular where you want to deal with this?
Another related question. Can anything be done about the scalar field? No spin at all.
So what happens is normally, from the logic that I'm going to present today, it doesn't seem as natural that you would like want to associate the same type of symmetries with it, because what ends up happening is you get these constraint equations, which you basically have because it's a gauge field. And so that's where, at least from this point of view, that's the natural case. I mean, there's a sense in which there's like a soft Fotino theorem that comes from looking at a supersymmetry multiple, and in that case you wouldn't expect there to be any redundancies to it. It's kind of
this triangle for the scalar
this triangle.
field.
I know, so the question is, it's not necessarily as obvious that there would be a triangle for the scalar field, because not only is it massless scattering, it's also, at least the way that I'm going to present it, it's going to be related to the fact that there's like this gauge symmetry and there's a memory effect that you can construct. So in some sense, it's going around in that direction. Okay, because so basically at the end of today, I'm going to write down some equations, and they're going to have a first order U derivative, and then I'm going to talk about what happens when you integrate against them over U. So, and you can construct some net observable, which is basically constraining the charges which are coupled to the gauge field to the actual gauge field itself. So you need that type of coupling, you need something charged under. And so the point is that scattering states are defined basically by like this momentum. You have some velocity and you have some charges. Say, maybe it's like E, maybe that's confusing with other soft momentum expressions. And so in some sense, like each of these variables ends up coupling to some memory effect. And it's because the scattering state is like defined by this is what comes out. Then you also know that there's a certain part of the gauge field that also has to have, like, I can take a charge, I can kick it, and I can kick it like really slowly, or I can kick it faster. But if I have an initial velocity and a final velocity that are the same, then I'm going to show that there's an observable that measures the net amount of radiation that is just fixed by that. But the power emitted scales like the square of the flux that you have when you accelerate, and so that can be scaled down with this slower and slower acceleration. So that's a kind of cool part about memory. But okay, okay. Great. So this is a very long metric, so if there's any more questions, it might actually be a good time if I can talk while I write and not mess up one or the other. So I'm going to take a pause for a second. I've just written down flat space in coordinates U, R, C, C bar. So I wrote U for flat space, and we're sticking with U in the radial coordinate rather than U and V together. And basically, I'm going to have one set of coordinates near future null infinity and one set of coordinates near past null infinity. And then the magic is matching them together when you talk about symmetry actions on null. So this is flat space with our funny conventions. And then we start adding more interesting terms. So this is a bonding mass term. So you can think of like if you had some massive object in the center, you would have some whatever r part of the metric corresponding to the curvature. So this is the metric at the leading terms in whatever r for future null infinity. And there's going to be a similar expression for past null infinity, which has some sign changes but it's good to write it up just because I'm gonna talk about C's and what's gonna be DZZ later, and we can just see what it is.
Sorry, I think my eyes are just letting
Oh.
me down. What's happening? There's
What's
1 over R, 4/3, NZ, minus
Yes,
a quarter.
Minus
what?
a quarter DZ.
Okay.
Yeah, okay, good. No, so call me out of that, and then it's good because I can write the next line, which is gonna be very similar, clear. So,
Okay.
which is, so this is the outgoing going to the same thing, so I like this a lot. Nice. Okay, so basically, thanks all. Think about how that is later. Great. So I want to now give an overview of how this type of metric is gotten to and more of an explanation because this was work done in the 1960s by Bonnie, Vandenberg, Metzner, and Sachs. And the point was to basically set up coordinates that are natural for allowing, when you're far away near null infinity, to have analytic Taylor series and 1 over R expansion for the terms of the metric. So you notice here we don't have any log terms occurring. And you start with your flat space and then subleading the 1 over R. So for the spherical part of the metric, you still have R terms, but it's 1 over R suppressed compared to the leading. So the kind of if you like go through their older papers, like the steps to doing that is basically setting so that if you have, say, an outgoing null trajectory, they're going to be at face u and theta phi on the sphere, and then so that helps set up the coordinates, and the radial coordinates defined in terms of like luminosity distance. So like the flux, like 1 over R squared for like the spherical angle, and then you end up writing. In their case, they were looking at Einstein vacuum equations. And so if you look at the 10 independent components, you have 6 of them that they start solving slice by slice in U as you go up. 1 of them kind of comes for free, and then 3 of them are going to be the constraint equations that I write down later. And basically in that case, those are only need to be solved at 1 value of R to hold. So there's this is the outline of the structure that they use for that. What else did I need to say here?
Excuse me.
And oh yeah, yes.
The second line of this matrix is to be thought
Uh,
as the same order as the bonding mass term or
So-
suppressed?
So the bonding mass term kind of comes with these, but the reason why I put out the second line is because it's complex. Because like the sphere you have z's and z bars that appear, so it's kind of, if I'm gonna like draw brackets and then add complex conjugate, I don't want to confuse with that term. But the bonding mass term and the News tensor term is like the radiation field. Bonding mass term and the angular momentum aspect, which appear here, and there, are supposed to capture the like this data that you have, like defining the charges at, say, spatial infinity. So what's going to happen is when they solve the Einstein's equations, they ended up looking at what, like you have certain equations and you're integrating them and they have integration constants, and some of them can potentially be the free data, but some of them are related by constraints. And so the essence of that is basically that the 2 degrees of freedom you have for, say, helicity, graviton state, are these CZZs that you see here. So just like tomorrow when we're talking about soft factors, and you're going to think of inserting some soft graviton, which is like the mode expansion of the linearized metric, then that's going to come from these components. So you can actually just change coordinates from h mu to the ZZ component and notice that one helicity or the other polarization.
Can I think about the second line as a perturbation from the background of the first line?
Yes, I would group this with that too, but let's maybe put it in red.
Okay.
So it's kind of, see, in some sense it is like a perturbation. I would say the more natural thing is and this is a good point, is that
The whole thing is perturbation.
the whole thing is a perturbation in the sense that it's suppressed in R. So in this sense you have flat space and this is like subleading. But what we think of as like, say you have a background metric and then you're like looking at acceleration or like small oscillations or linear perturbations around it. I would think of this as like the radiative, like the independent component. And then we're gonna see that these guys are related to some net effects from these. But in a sense, yes, if you had just some background that wasn't like with some massive term, then this would be like the part.
So
of
this
it
term
that's
should be
like-
the leading part of the perturbation, that's right? The MB
Yeah,
is
yeah.
the whole mass inside
Yeah,
the background.
True, as far as like, actually like what you, like, so say you're like, you have not flat space, you have something sitting there and then you see like basically how you'd be attracted inwards, that would be like the mass term. But there's a sense in which the degrees of freedom that we want to look at like quantizing are these terms, that's why I'm just pointing out.
I mean, it's
Sabrina,
whatever.
why don't you tell us how MB changes with time?
Yes,
Because that will.
I want to get to that at the
Okay.
end though. No, I will, okay, it's gonna be, there's gonna be du, mb, okay. For Malcolm, I'll give a partial spoiler, I guess, because why not? So partial spoiler, I'll write this again later. GMB. I'm going to define what this is. This is appropriate radial like components picked out part of the stress tensor. But you basically get an equation like this. So if you just think of a static like situation where you have some like mass sitting there, then you wouldn't, then you can just like have a term like this. But the point is that if you have something where there's radiation and there's mass loss, then these terms in the metric are going to change as a result of it. And so there's a sense in which this is going to be the origin of like the memory effect because
What
it's a first order equation.
is the du
du.
in front of
du, bonding mass, which is the
and later on in front of C's and
Oh,
du
yeah,
as well.
there's a du here too. Du here and then du.
Sorry, in the TUU? Is
Yes.
that just from that?
No. So I'm gonna write this out more, I can write it down now.
So it should
So
be
TUU is 1/4 du CZZ. Du CZZ. That's 4 pi. du. So basically, there's one nice way of kind of packaging it. You have nonlinear terms in the metric, and you can pull them back into what you define as a stress tensor. So in the sense of what we're looking at is, in our case, scattering, where we're like kind of probing with the single soft graviton insertion. And you can imagine that if you had some more energetic processes, so like the particles that scatter, say, sourced something, some part of the stress tensor coming from the metric itself could also incorporate it. But in this case, it's kind of like a way to separate out and still see the memory effect even in its full kind of nonlinear glory. And so Christodoulou and friends had like thought about packaging it this way too. And so it's kind of a nice grouping for our purposes. Okay. Good. Any other questions?
How much are Einstein equations used just to write that metric?
So what happens is it's written in a much more complicated form to start with. You end up assuming some ansatz where once you have chosen your coordinate system to be u, like theta and phi for outgoing geodesic, that'll restrict certain connection components so that that stays as a geodesic, so u equals constant on the trajectories. And then you have some overall like scale term that you allow, and solving them together is what gives you, these are basically the integration of the constants that come out that are undetermined, and that then like you rewrite them in that form. So this is like a simplified.
Einstein equations are used here already.
They were,
Or this is just a choice of coordinates?
so, well, it's a choice of coordinates as far as I'm concerned. But how they were originally derived was that Bondi, Vandenberg, Messner, and Sachs were looking at the space of solutions to Einstein's equations and trying to see if they could pin down, well, one part of it is pinning down, like, now that you have this metric, the next step I'm going to talk about is how do you keep this form of the metric? Are there any other diffeomorphisms that keep you in the same radial fall-off scheme? And so if you want to study like how close you can be to like not exactly flat, then this is the form that you get as a result by studying the solutions, but the point is that you still have, like I haven't imposed Einstein's equations in this. Yeah. But
And there's
the
an
form of the
asymptotic
fall-off.
Einstein condition in the sense that if you imposed it to first order or something at infinity, second order.
Like this will basically make sure that you don't have too much, like so for in the electromagnetism case, you don't want to have like too large a fall-offs in the radial field because then you have like some infinite energy, which can just like some too much. So that type of logic is what's giving you like the what order in R appear and stuff like that. But so in the original setup, they are like solving parts of Einstein's equations and looking at the set of solutions and what the free data is. But that is to get to this form of the metric. Okay. Yeah. Okay. There. Great. So before I go back fully to the constraint equations, which are going to be a nice. We're going to look at what you can do to stay within that form of the metric, but still have some freedom in coordinates. Might be. Cover half of it and just talk about. You see that? Okay. And write down the. So there's going to be some. Asymptotic the vector field time. And this takes the following form. Okay, so I've written down a vector field that has two things parameterizing. First of all, you have y, and yz is going to be some function of z. So this is an extension of the original asymptotic vector fields, which are just parameterized by f, which is a function on just a real function on the sphere. So I'm going to talk a little bit about where these appear and basically, so you have this one with a metric, and you have, say, this ansatz. Well, this one's its ansatz, but you can actually like derive it by looking at the fact that you only want take the Lie derivative along the vector field of the metric and look at the components, and you don't want the components to change to a different order in R. So you don't want it to be larger than this set of fall-offs. You want to stay within that ansatz. And so you work that out, you end up originally with this solution with just f here. And so if we take a step back and just imagine if we convert coordinates between the u, r, z, and z bar and x, y, z, t, you'll find that translations are a part of this, but this is actually an extended thing called super translations. So you have an arbitrary function on the sphere, and the ways that people originally kind of thought of it as that this is, say, F says how much you're translating to U. So if each generator normally would go out at U, and this is going to shift them a little bit at null infinity. But say Barnich's work and also Banks in the past maybe like decade or so suggested that you could extend it to also have infinitesimal super rotations. So you have the global Lorentz transformations if you look at up to quadratic order in Z. And so it's a real vector field, so Y Z bar is like the conjugate of it. But in some sense, because you have this sphere that's an S2 at null infinity, you can think of it in terms of potentially not just having Lorentz transformations, but also full Virasoro. And so that was kind of the origin of why it's kind of cool to look, first of all, and focus on four-dimensional scattering, and also why this whole system of like having these asymptotic symmetries that you care about was potentially interesting because there's some work right now where we're trying to think about how much advantage we can take of the fact that we don't just want to maybe look at things that are globally defined in the sphere, which would just be Lorentz invariance for scattering prop matrix. But also, if you think of like where the punctures where this would perhaps break down as being where particles exit, then maybe it's natural to include that too. So, any questions, at least about this vector field that's being written down? Good. So, we have that. So now, I guess what I want to do is just erase some of the stuff we did. So, once we've gotten to this point where we have some form of the metric and some asymptotic Floyd vector field, the essence of some of the work that's been done by Strominger and collaborators is to construct this Ward identity, which was the original connection between soft vectors and symmetries. And the point of it is that you have this transformation that's changing, say, in this case, they're at future null infinity. And you have a similar one for past null infinity, but the choices of the F's and the Y's should be connected so that you're not doing them separately. So in that sense of looking at it as symmetry, is essentially the origin of this picture of this Ward identity. So we have a vector field, and if you look at the charge that it generates, so in terms of like you have some phase space determined by these radiating degrees of freedom, then you can try to split it out into components that look at what you do to past null infinity and future null infinity and match them together, and that's where the soft vector terms are going to appear, in addition to terms relating to actual scattering processes. So that's hopefully where we get to in the end. So what do I want to write out? For example, the charge for the case. So I only wrote one equation down, which is me. I can try. So you have the metric and you have a few equations that are in terms of Einstein. So this is just G mu is equal to 8 pi G T mu. And for our case, the null generator, so along null infinity, is a vector du dr for flat space, but you write it in tetrads to take the form of the metric and actually evaluate it for the full case. But this is just to show that the relevant components of this equation that are the constraint equations are basically the G du and G u z, which is what I'll write out next. And then again, T, in our cases, we're always kind of grouping together the nonlinear terms with them right now, and we can talk about it more if the others. And I've defined MZZ as du of CZZ. So, I guess we should just pause and get this for a second. So I kind of explained a little bit about the body master before. This is the exact same thing that's going on with the GZ. Now, if you notice, in each case, there are kind of three terms. If we put this all together in our fine, just calling that like the hard part of the stress tensor. So three terms are good to individually look at because when we write expression for the charge, it'll set things up nicely for all this memory effect stuff tomorrow. So the first part is this first time derivative in u that's appearing. Then in that case, one can imagine, say I integrate this along u, and I have two things. So there's a sense in which at a future time like infinity or near that, so like the future limit of future null infinity, I could have some boundary conditions, say for instance that basically everything's left the system and it's radiated out. And same thing could happen, I could set up for past null infinity, the analog of this for V, and then at near spatial infinity, there's a potential to match the two. So that type of setup, if you have some specifications for how the fields along null infinity kind of fall off along at like extreme limits of retarded time. And same thing in the time reverse setting for advanced time. And then some matching condition across I naught. Then there's a sense in which I can take some expression like this, and when I integrate it, I have one value going to 0. So say I construct du of du and b from infinity to infinity. This is just going to be MB evaluated at, I'll write my notation that is consistent with what's seen. So I have that. And then if I'm doing the same thing for the equations at past null infinity, one of these terms, I could say this is equal to 0 by some boundary conditions. And then this term, say, will be equal to the same expression in the past. So if I relate them, the two, I'm going to basically get an expression where this guy in the future is related to this guy in the past. And now that statement is a statement about the radiative degrees of freedom that you measure, so net zero mode of those, and the scattering process. So that's going to be like the essence of understanding the memory effect, understanding the word identity is a setup where you have whatever matter is going through future null infinity and past null infinity, because they have the other side of the equation. And the radiation that's sourced by that, there's some net memory effect that says, I measure this observable, and it corresponds to what happened in my scattering process. So the scattering process conditions the particular observable. Is the origin of that. Great. So one other thing to point out is if I just write out the expression for the charge, say. The super rotation. So, suppressing some quadratic terms, but like work of Barnich isolated what the charge corresponding to the super rotation vector code, so this first line, corresponds to. And if you look, there's basically this overall U derivative hitting the volume mass and the angular momentum aspect. And then if you're worried about this one term where it hits the u first, you can actually see that that cancels between this guy appearing and the fact that du hitting nz is going to give you dz of mb here. So that's nice. And so, in essence, this is the charge that you're matching at spatial infinity to then create it so that you have an equation which is just this right-hand side related between the two sides. And that leads into what I'm going to talk about tomorrow, which is the memory effect. And so at this point, I felt like, since it was either discussion or like the two-part thing, this is like the ugly part that's kind of like getting through the nasty details. So the essence of what I wanted to set up was some notion of null infinity in the sense of like it's an arena for scattering. So we have a picture of flat space, and what goes in, what comes out. When it's massless, is going to hit these boundaries. So there's kind of this space-time interpretation of where like the initial data kind of and final data kind of lies. And we also have a notion of the asymptotically flat metrics. So why this is interesting, not just in actual flat case, but when we add gravity and went through the details of what symmetries preserve that form of the metric, not keeping it exactly as it is, but changing it within the same scheme, and got through what exactly those were, what the charges were, and how you end up in a gauge theory, is in this case gravity, having a constraint equation that gives you something where you have some net matter and radiation that are going to be related to each other that cause the word identities to work out, because you basically have this constraint equation. So I think that I want to like turn it into like if there's any questions, just because like the stuff with tomorrow with memory effects should be much more kind of intuitive and fun to play with, because you basically start with some first constraint equations that are like a first order time derivative. You've integrated them along, and you have some. Now that I've integrated a long time, you can imagine this is like the radiation field, but it's a time integral, so it's going to pick out low frequencies. So you can see where naturally you're going to get the soft factors with the residue of the pole, or actually like at omega goes to 0, just because you've had to integrate over time to pick it out. But then it's also related to the scattering process. And so in this case, TUU would be like the energy for the particles. And then you also have the angular momentums of like the velocities of the charges, or some orbital angular momentum. And then a similar thing with the gauge theory case, just to keep it together. So that kind of fits nicely in something, but this is like the setup. So
what happens to GUR constraint?
GUR. So
part of my equation.
so
Is that
those aren't really like. Okay, so there's a sense in which these are like the ones that you want to impose from the beginning are the first order and new ones that are constrained along null infinity. So this is like, and in this flat space, this would be the null generator along null infinity. And so it's kind of analogous to, except for the fact that you can actually have like causal propagation along null infinity. Like if you had your 3+1 splitting and just talk about like a space like Cauchy slice, then the constraint equations are kind of what has to hold on the slice, and then you evolve off of it. So you don't want to impose all of the equations in motion on the theory if you want to think about these as still being like the modes that you quantize. So the other components, if you were solving for the full theory, would be there, but these are the ones that are like, you solve it just at one value of R, or in this case at null infinity. And like if it holds on one slice, then it holds its consistency. And then the rest of them are like the other Einstein's equations that aren't just first order, they're second order, and like that's what we quantum. So if you isolate these,
usual
really
spatial
good.
like we have 4 constraints.
Yeah, so what happens is one of them is like the R component ends up falling out in the way that we set up the metric. Yeah, so it's like, so you have 3 here, so you have 2 and 1, and then the third one was when I talked about solving it, I was like, there's one that's free. So this is like the fact that you've set it up so that the metric stays GU, GR is sub R is 0. So it's fine.
So if you look at the grouping, then so you've
Yes.
grouped in the stress energy on the sort of line above a gravitational term.
Yes.
So in some sense, you saying that the gravitational term that you group with the matter is in some sense the source-like behaviour of gravity, and then the stuff above is the radiative part. Is that the way that you're trying to
So the way of,
separate it?
in the sense that, okay, so say I was looking at a linearized perturbation and see this one is really small, then this would be even smaller. So it's kind of like separating out. But you can imagine that there's a sense in which if something gravitational did source the effect, you could still group it this way, and this is what you observe. So for instance, part of what I'm going to get into tomorrow is picking out what your observables are, so what can you actually play with. And so for the gauge theory case, you want to measure something physically, you want to measure like an electric field, but once you've picked your gauge choice, you can see what that is in terms of the connection that you've written down. So in this case, CZZ is a component of the metric here. So if you can look at deformations on this sphere, that's how you would probe it. And so there's a sense in which once you connect some observable, which is what I'll set up tomorrow, to it, then you'd still see this part depending on whatever this is. So if you group it together, then if you're actually probing like changes, that's what you would see.
I mean, maybe it's another way of
Yeah.
thinking it that term you've written in TUU is the integrand of the Bondi mass loss theorem.
Yes,
So
exactly.
it's
It is.
natural to think of it as an energy density,
Yes.
right? So that's why you would think of it as a.
Yeah, and it's kind
Right,
of
right,
cute too,
right.
because one thing here, which is fun to point out, exactly in that situation, this is the same thing where I was talking about in radiation for like just a charge that accelerates, how it's proportional to like the square of the radiated electric field. And so in this case too, here you see that if you have CZZ, however it's sorted, and it changes to some
Yeah, I mean,
specifically, the square can be suppressed, say, in a radiation percent, but if you fix the boundaries, then like you still have this term. So there's a
Yeah, I mean those terms integrate to zero, and I guess the point is.
but they don't integrate to zero. That's the point.
Well, sorry, they.
Yeah, the
It's zero around the sphere.
See, no, it's around the sphere, yes, exactly. And so that's where
and
it.
so as you say, it's the Bondi mass loss there, and then what you do see is the positive term, which gives you the sign. Yeah.
But the fun thing about it is it's exactly precisely the fact that they generically wouldn't integrate to zero, which is why this memory effect stuff is important. So, in some sense, we literally have.
Isn't the point that this shows you have energy conservation in every direction rather than total energy?
I really like that's the way that Andy loves thing. I personally like the memory effect notion. See, okay, I'll tell you a little bit of a preview, I guess, for next time. There's a sense in which if you have say you have a mass or you have a charge and you boost it and you look at its like say radial electric field, there's going to be some angle dependence because it's basically pancake because you move it at some velocity. So now you have that angle dependence, and you have a set of scatterers for your in states and your out states that all are going in different directions, and so you can build up this arbitrary angle dependence still in like in the field that's non-radiating. And then now you have some net change, and basically there's a constraint relating the gauge field that you measure at every angle to the charges. So whether or not you want to, like in some sense it's like a definition of what you want to call like the energy, or what, like the fact that there's a metric response at every angle that you can see what is scattered is kind of like the origin of that. It's not, like normally if you take this equation and you said, okay, so this guy, for the super transition case, this gets replaced by F. There's no U here. So basically the body mass term is like the charge. And normally I'd say, oh, only the global charge is conserved, so I just integrate it over the sphere, and I lose this part of the data. But I have like net charge conservation or net mass conservation. Now, what happens here is if I then allow an arbitrary function here, then naively, you wouldn't necessarily have, like you wouldn't think that would be, say in the gauge case, like you only want to allow like overall change in phase, not an arbitrary function in sphere. It wouldn't pick out anything interesting, but it actually does because basically the fact that this part of the metric is constrained to have a certain form that actually is given by the soft factor. So you can literally plug in, tomorrow I'll plug in the expansion of the metric, look at the soft factor that comes out and see that it matches this part of the scattering. So that's the sense in which you kind of motivate keeping these large, this charge with the arbitrary function in front of it would correspond to a large gauge transformation super translation. And that's just kind of changing your coordinates in a different way at each angle at a sphere, but you can't just say, oh no, I want to stick to flat space as it is, or like some particular choice, because even though if you did that at one point in time, if something else happens, then any scattering process is generically going to change it. And so that's kind of the motivation for why you want to include these large gauge transformations, not large in the sense that it's topologically distinct, but large in the sense that it doesn't go to just a constant on the angle. So even though there's a part that's just pure gauge, there's a part that is a step function, essentially. Or at least somehow it ends up being like a step from one reason to another, and that's physical, that's observable, that's told to you by the scattering process, and this is going to be the heart of tomorrow, which is so.
I have another question. Do you know, or will you be able to write quickly analogs of these for U1? So what's the asymptotic expansion for the U1? I don't know if you have them.
No,
If not,
no, I mean, I have this right here. I'm just going to grab it from a different sheet of paper.
also what's the analog of asymptotic symmetries in the U1 case?
I want to draw.
These two lines.
No, it's really short. It's just need to right click. So this is going to be an uglier form of it. But there is a sense in which you're interested. Symmetric hemisphere is going to be the same. And I haven't yet decomposed it into different orders and whatever arm. So basically all I've done is written out, you have your J mu in terms of gauge field, and I contracted it with the n that I defined before, because we're actually in flat space, I need this to be, so in this case I just wrote down the u component, but if you look at the contraction, essentially if you look at then expanding these guys in the radial behavior that I expect for radiation field, this is the expression that's going to give the term. And so there's one paper, which I have, which then turns this into a rather nice form for the memory effect, which is kind of simpler. So,
Actually,
what this
my question is, in the graviton case, you have super translations, super rotations. What are the analogs of this in the
it's
U1 case?
a largely one. So,
What are they parameterized with?
they're parameterized by a function in this here. So the closest analogy is to the super translation case, because in that case you had bonding mass and you multiplied by an arbitrary function on the sphere. In this case, it's like taking the zero component or the u component is like the electric charge that you normally integrate over the sphere, and multiply that by an arbitrary function. So it ends up being fu, like the radial component of the electric field times an arbitrary function instead of whatnot, and it gets a relation at each angle that's similar to this. And so I wrote delta here because this is the same thing as integrating along u of the AU component. Same thing with the Z component. So if I look at the same expression for gravity, it's pretty similar. So just imagine this one, if you integrate along u, replace d by du with a delta, and you get that expression where now the charge is like this guy, and AU is like the normal electric charge gauge field component, which is like the radial electric field is going to be parameterized by this guy. So there's a similar form, but I just wrote deltas instead of d by d's because I integrated along there. And so you're asking then what it corresponds to is this large U1, and what, basically, so as a little preview again, maybe for next time, is that you have, like it's just a gauge transformation. So you've set up maybe like, okay, I don't want to like have arbitrary functions that are pure gauge that have some random radial fall off that doesn't match at all with the physical thing. But there's a sense in which when you have a scattering process, there's going to be some, whatever our radiation field you measure. So you sit far away, something goes by, like a radiation happens and you see it. You've measured to whatever our field, you integrate over time. And during the period of time where you have flux coming at you, you're going to see something, but in between it's going to be like as if there's nothing. So it's like there's no electromagnetic radiation hitting you for, say, some interval. Then it's pure gauge in some sense. You could like change your coordinates so that it's back to just being 0. But in some sense, the fact that there are transitions that are related by a certain behavior, like in this particular whatever our mode of the gauge field, you kind of, okay, it's like a step function, and then you, so say I am going along and I see some radiation and something's changed by that amount. My large gauge transformation is just basically, this is at any angle on the sphere, so I'm a sphere and I'll move at a point. And I see radiation field, I've measured some time interval of the radiation and it's changed, but I have the ability to just pure gauge transform and move it up or down, change my baseline. So I can imagine, say it's 0 here, and it was non-zero here before, or it's 0 here, and then it becomes non-zero. And in a sense, this is like taking the Fourier transform of a function that doesn't decay to 0 at both endpoints. Like, so it's an overall shift. There's a delta function part, and then there's a pole that in the frequency corresponds to a step function. And in some sense, the residues of these Weinberg poles are like the step function, this memory effect. And then the pure gauge is like the overall constant along mu mode, which has a corresponding action along past null just because you don't want to change things separately.
So, is this all you wanted to say today?
This is all I want to say today, because this stuff is like
That seems
the
amazing.
setup.
Thanks very much.